arrays are also a common construct used in high-level programming languages. It allows us to access large amounts of similar data. So we have an array with an index that gives us the number of each element, and the size. We have to know how many elements are we storing. So here is an example array. It's a 5-element array, has some base address, and it has then 5 elements. So this index number right here, this is the index number, index 0, index 1, index 2, 3, and 4 gives us the element number. And so index 0 of that array starts at the base address, and 4 bytes later is index 1, and then so on. And so we have a size, which is 5-element array, and these are 32-bit words. And then we're going to store it somewhere in memory. And the base address is the address of index 0. So array sub 0, bracket 0. So our first step in accessing an array is to load that base address, and then we can access it using an offset. So that base address plus 4 gives us the next element, base address plus 8, element 2, base address plus 12, and base address plus 16. So here's an example where we still have our 5-element array here, and we want to multiply array element 0 by 2 and put it back in that array element. And array element 1, want to multiply that by 2 as well and put it back in that element. And so we're going to load the base address into register S0, and then we're going to access these values. So first of all, we can perform, load upper immediate into S0, this base address register that we've chosen, hex 1, 2, 3, B4. That's the top 20 bits. And then add immediate to get this 32-bit immediate into S0. Add S0 to hex 7, 8, 0. So now S0 is going to have going to hold that entire base address. And so the first thing we need to do is we need to load the value currently in array sub 0. And so we're going to load word into somewhere, let's say T0, 0 plus the base address plus S0. So now T0 has the data, it's not shown here, but whatever data is held at that memory address. And we want to multiply it by 2, so we're going to shift left logical immediate. T0 by 1 bit multiplies it by 2. And then we're going to store it back into, after we've multiplied it by 2, back into the memory address for index 0 of the array. Well, and now we want to do that again for array sub 1. Well, now we can do very similar code, load word T0, we're done with T0, so we can overwrite it, but now we have the offset of 4, because we now want to access the base address plus 4. Right, here's our base address plus 4. And here's 4 plus our base address. And now we're going to shift left logical immediate, T0, T0, 1, to multiply that data value that we just loaded from memory. Now we're going to store it back into the same address, the base address plus 4, to access index 1. And here is the code written more neatly. It looks like in this code it uses T1 instead of T0. That's fine. And there we go. So we can access memory, and we can access these arrays in this kind of orderly fashion. If I had to do this for, let's say the array were 100, had 100 elements. Well, I have to do this. If I want to multiply each of the elements by 2, then I perform that code instead of just 2 times, 100 times. with a different index. The index is 0, and then 4. The next one would be 8, and then hex C, and then hex 10, and blah, 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 until I get all of my 100 elements that I load, I read, I multiply, I shift left logical by 1, and then I store back. So it starts to get tedious, right? It starts to be what we call code bloat, right? We get a lot of code to do. 2 is fine, but 100, what about 1,000? What about 10,000 elements? Now this code just is just becoming more and more, it's bloating. So we can actually use a for loop to access our arrays. And so this is a common construct. Let's say we have an array with 1,000 elements, and now we're going to perform some operation on them, multiply them by 8 in this case, and store it back into memory. And we want to do that for each of the elements, 0 to, well, 999. And that's where people often get off by 1 on their index. They think, oh, it's a 1,000 element array. The highest index is 1,000. No, the highest index is 999. Okay, so while I, or for I equals 0, while I is less than 1,000, it's going to keep doing this and incrementing that loop counter, or that index counter, to say, okay, I plus 1 until we get to 1,000, and then it is done and says, oh, I is not less than 1,000 anymore. And so here we have our base address. In this case, our base address is 23B8F400, and we could actually use that or immediate. More common, like we've shown, is to use add immediate, but or immediate actually works as well. And then in this case, and then we're going to initialize I and initialize some temporary register with 1,000 so we can compare with it. And again, we're comparing that opposite case of branch greater than or equal to our condition was as long as I is less than 1,000. Want to keep doing the loop operations. This is our condition. And so we're going to test the opposite case. If I is greater than or equal to 1,000, then it's going to say I'm done with this loop. Keep going. And now we have this this index I is going 0, and then incrementing 1, 2, 3. Those are the indices of our array, but the address offset, that byte offset, is multiplied by 4. So right, it's going to be 0. The next element is address 4 above that, and then 8, and then 12, blah blah blah. And so we multiply it by 4 first. I times 4. So shift left logical immediate by 2 multiplies it by 2 to the whatever we've shifted it by, in this case 2. And we put that into T0. Now we're going to add our base address, S0. Remember we loaded S0 with our base address. And we're going to then add that offset here. So now we have the address of array sub I. So in the first case, it's S0 plus 0. The next case, it's, well, index I is 1. And so 1 times 4 is 4. And we're going to get 4 plus the base address. Next time, index is going to be 2. But 2 times 4 is 8. So we're going to get 8 plus the base address, and so on. And then we load. This looks familiar. Load at that address, which is now the base address plus 4 times the index. Shift left logical immediate multiplies array sub I times 8, and then we store it back into that same address we calculated, and we increment the loop variable I equals I plus 1, and repeat. Check the condition, repeat the body of the for loop, and continue until I is greater than or equal to 1,000. One common array that we use is to store strings of information. So we use ASCII encoding. ASCII stands for the American Standard Code for Information Interchange. And this encoding gives each text character a unique byte value. So for example, capital S is equal to hex 53, little a is equal to hex 61, and big A is equal to hex 41, and so forth. So we can encode characters using binary values, using bytes. And turns out that lowercase and uppercase differ only by hex 12 or hex 20. So it's easy to change from all lowercase or all uppercase. And here's the table of all of the ASCII encoding. So for example, the right parentheses is hex 29, little g hex 67, little k hex 6b, and we can see that big K is lower by hex 20, it's hex 4b, and so forth. And so we can have an array of characters where we, want to store the value start or something, START. And so we can encode that by looking, okay, well, let's see, the 8-bit value S is hex 53. So in memory, we'll put hex 53. The next byte will be lowercase t. We go look over here and look, it's 74. The next one is hex 61. Next one is hex 72, and then another hex 74. And so we can encode that string, and then in C, the string is at the end, so we have our number of bytes. In the case of start, we have START, 5 bytes of information, and then the last byte is called the null byte, or 00, to indicate, hey, this is the end of that string. Don't keep reading. And so in this case, we'd use an array of bytes, not of words. So then we'd want to use load byte and store byte instead of load word and store word to access that array.